Vertical farming is one of the most ambitious attempts to redesign agriculture for the 21st century. The concept is straightforward. Grow crops indoors inside stacked layers using artificial lighting, climate control systems, automated irrigation, and precisely managed nutrients. Supporters argue that vertical farming can reduce land use, eliminate weather risk, lower water consumption, shorten supply chains, and bring food production directly into urban areas. Critics argue that the model struggles against basic economic and physical realities, particularly energy consumption. The central question is no longer whether vertical farming works technically. It clearly does. The question is whether it can scale economically enough to meaningfully contribute to global food security. Traditional agriculture relies heavily on free natural inputs. Sunlight powers photosynthesis. Rain provides water. Soil stores nutrients and supports root systems. Vertical farming replaces most of those free systems with controlled industrial infrastructure. Artificial lighting substitutes for sunlight. Pumps circulate water and nutrients continuously. Air conditioning systems regulate temperature and humidity. Sensors monitor growth conditions in real time. Every variable becomes controllable, but every variable also consumes energy and capital. The strongest advantage of vertical farming is efficiency per square meter. Because crops are stacked vertically, output from a small urban building can exceed the productivity of a much larger traditional field. These systems can also produce crops continuously throughout the year without seasonal interruptions. Pest exposure is reduced because the environment is enclosed, allowing some farms to minimize pesticide use significantly. Water efficiency is also much higher than conventional farming in many systems because water is recirculated instead of lost into surrounding soil. However, vertical farming performs best with a narrow category of crops. Leafy greens, herbs, microgreens, and some small fruits are currently the dominant products because they grow quickly, require relatively low energy input, and generate high market prices. Lettuce, basil, spinach, and similar crops can be profitable under controlled conditions near urban markets where transportation costs are high. The problem emerges when discussions shift toward staple crops capable of feeding populations at scale. Human civilization is sustained primarily by calorie-dense staples such as wheat, rice, corn, soybeans, and potatoes. These crops require large amounts of energy from sunlight over wide areas. Replacing sunlight with LEDs for staple crop production creates a major energy challenge. Photosynthesis itself is not highly efficient, and artificial lighting systems add additional conversion losses. Electricity must first be generated, transmitted, converted into light, and then absorbed by plants. Every stage introduces inefficiencies. This creates the central paradox of vertical farming. The system can maximize spatial efficiency while simultaneously struggling with energy efficiency. Sunlight delivers enormous amounts of free energy to agricultural land every day. Replacing that natural process with industrial lighting dramatically changes the economics of food production. Even highly efficient LEDs consume substantial electricity when operating at the scale required for mass calorie production. Energy costs have become one of the defining pressures on the industry. Several high-profile vertical farming companies expanded rapidly during periods of low interest rates and optimistic investment conditions. Many projected that advances in automation and lighting efficiency would eventually reduce operating costs enough to support large-scale profitability. Some companies succeeded in specialized markets. Others accumulated heavy debt and faced financial collapse when energy prices increased or investment slowed. The economics of indoor agriculture are also heavily affected by geography. In regions with abundant renewable electricity or low energy costs, vertical farming becomes more viable. In dense urban areas with high land values and strong demand for fresh produce, Local indoor production can reduce transportation expenses and spoilage. But in regions where energy is expensive or electrical infrastructure is unstable, the model becomes significantly harder to sustain. Automation is another major component of the industry. Advanced facilities increasingly use robotic systems for planting, monitoring, harvesting, and packaging. Artificial intelligence systems analyze plant growth, optimize nutrient delivery, and adjust environmental conditions dynamically. This reduces labor requirements and increases consistency. However, automation also raises capital costs substantially. Vertical farming facilities often require large upfront investments before generating any revenue. The environmental argument surrounding vertical farming is also more complicated than early marketing suggested. Water consumption is significantly lower than many forms of conventional agriculture. Land use can also decline because food production is concentrated vertically rather than spread horizontally across large areas. Reduced pesticide use lowers some environmental risks. Yet these benefits must be balanced against electricity demand, construction materials, cooling systems, and the carbon intensity of local energy grids. Transportation efficiency remains one of the industry's strongest practical advantages. Traditional agriculture often relies on long global supply chains. Produce may travel thousands of miles between farms, processing centers, warehouses, and supermarkets. Vertical farms located near cities reduce transport time dramatically. This improves freshness and reduces spoilage losses, which are a major issue in global food systems. In some cases, reducing waste can partially offset higher production costs. Climate change is another factor driving interest in controlled environment agriculture. Droughts, floods, heat waves, and changing weather patterns are increasing agricultural instability in many regions. Vertical farms isolate production from external climate conditions. Crops can be grown consistently regardless of drought or seasonal variation. This resilience may become increasingly valuable as weather volatility intensifies. Despite these advantages, vertical farming cannot currently replace conventional agriculture at global scale. The caloric requirements of billions of people remain too large. Producing staple crops indoors using artificial lighting would require enormous electrical infrastructure. The energy density provided freely by the sun across traditional farmland remains extremely difficult to replicate economically inside buildings. This does not mean vertical farming has failed. It means the technology is likely to occupy a more specialized role than some early forecasts suggested. Instead of replacing traditional agriculture entirely, vertical farming may become part of a hybrid system. Indoor facilities can supply high-value crops near urban populations, while traditional farmland continues producing staple calories at large scale. The future of agriculture may involve integration rather than replacement. Research continues to improve efficiency. LED systems have become substantially more efficient over the last decade. Plant genetics are being optimized specifically for indoor environments. Better climate control algorithms are reducing energy waste. Renewable energy integration may improve long-term economics in some regions. Nuclear-powered industrial agriculture has also been proposed as a possible future model for large-scale controlled environment food production. Government policy may also influence the sector heavily. Countries concerned about food security, water scarcity, or supply chain resilience may subsidize indoor agriculture strategically. Nations with limited arable land but strong energy infrastructure may view vertical farming as a national security investment rather than purely a commercial business. The debate surrounding vertical farming often becomes polarized between technological optimism and economic skepticism. In reality, both sides identify legitimate factors. Controlled environment agriculture solves several serious agricultural problems simultaneously: water efficiency, pesticide reduction, climate resilience, urban proximity, and land conservation. At the same time, physics imposes real constraints through energy requirements and thermodynamic efficiency. The most realistic future is probably not one where vertical farms replace traditional agriculture, but one where agriculture becomes increasingly diversified. Open field farming, greenhouses, precision agriculture, gene-edited crops, robotics, and vertical farming may operate together within a broader food production system optimized for different environments and economic conditions. Feeding a growing global population will require more than a single technological breakthrough. It will require balancing energy systems, water availability, transportation networks, land use, and agricultural productivity simultaneously. Vertical farming addresses some of those pressures effectively. Others remain unresolved. The central paradox remains unchanged. Vertical farming can grow food with extraordinary precision and spatial efficiency, but replacing the biological and energetic advantages of open sunlight remains one of the hardest engineering challenges in modern agriculture. The future of the industry will depend less on futuristic architecture and more on whether energy economics can eventually support food production at truly global scale. If you enjoyed this deep dive into the forces shaping our future, be sure to explore our other documentaries examining the technologies redefining modern civilization. And if you want to keep exploring the biggest questions about science, power, and the future of humanity, make sure to subscribe to the channel and join us for the next journey into the unknown.